For this video, I'll be working through the 2018 Level 3 Mechanics exam, question 1. Question 1. The electron rocket developed by the NCEA company Rocket Lab has begun commercial launches of satellites from Mahia Peninsula and Hawke's Bay. The rocket can carry a satellite of mass 150 kilograms or 1.5 times 10 to the 2 to a stable circular orbit of 5 times 10 to the 5 meters above Earth's surface. Show that the force due to gravity on the satellite in orbit is 1,270 newtons. So in your formula sheet, you'll have gravitational formula, which is right there. We're going to write that in, plug and chug, and away we go. We see that there, right? Fg equals gravitational constant, the large mass, the small mass, divided by the distance between the two masses squared. That's going to be 6.67 times 10 to the, negative 11, times mass of the Earth, 5.97 times 10 to the 24, times mass of the satellite, 1.5 times 10 to the 2, that's just 150 kilos, divided by, and here, meters, kg, sweat. We haven't been stumped with any kilometers anywhere. Above the Earth's surface, and that's the radius of the Earth. So we need to add those two together because it's from the center of mass of both objects. It's the center mass of the Earth to the center mass of the satellite, which is way up in orbit somewhere. So 6.37 times 10 to the 6 plus 5 times 10 to the 5. I'm just skipping a whole lot of numbers because it's easier. Equals 1,265.54. which I calculated just before, and you can round that up to 1,270 newtons. There we go. Try and keep it all on the top line, keep it neat, so you can leave this, if you don't need to, leave this blank, so examiners don't, it's easier for people to contain. Right. The rocket, the satellite, and any space debris at the same altitude and circular orbits will travel at the same speed. Show that this is always true by deriving the formula for orbital velocity. Right, so straight off the bat, that's the incorrect formula. They stuffed up a few questions on this exam. But anyway, so that should be the large mass of the planet, not the small mass, and we'll get into that soon. So you just got to show that the centripetal force, or the center pointing force, is going to be equal, which is called the centripetal force, but in this case it's gravity. Fg, and then you write mv squared over r is going to be equal to big G, big M, little m over r squared. In other words, divide both sides by the small mass, so you get v squared over r is going to be equal to big G, big M over r squared. In other words, move the r up onto that side, so you cancel out the r squared underneath, and square root both sides, so you get v is equal to square root big G, big M over little r, just times both sides by r, and that got rid of that r, and that got rid of the squared. And there we go. So that shows that, although this is obviously not correct, it should be big M. If you actually print it out, or so this is the printed copy that they released a while ago. I just do this first. It's actually big M, but in the exam they gave it as little m, and I obviously use the exam papers because I like to be neat. Right. So, and use this to determine the orbital velocity of the satellite. So we have to find out the orbital velocity, v orbit. Let's get v orb equals square root. It's a pretty hideous square root. 6.67 times 10 to the negative 11. We see that. Times mass of the planet, 5.97 times 10 to the 24 divided by 6.37 times 10 to the 6 plus 5 times 10 to the 5, and that is going to give me 7613.27 meters per second negative 1, which is pretty much equal to 7 0.610 meters per second, -1. Notice how around afterwards I leave the unrounded number there. I've left no gaps, so if the marker is coming to contain it, you can just circle this whole lot, and then you can just put a line, and then so I'll show if you're containing a paper like that, and it's easier for the marker. Trust me, I marked waves, and it's just so much nicer when people do that. Right, 20 kg piece of space debris is traveling at the same altitude and speed as satellite. But just a side note, if you use little m and you got a funky answer, they only gave you this is pretty ruthless, this question. They only gave you achieved if you didn't pick up this, even though it was their mistake in the exam. But yeah, so it probably doesn't really matter to you guys, but if there is a mistake, you've got to find it, and you've got to be able to maybe just say that it's a mistake. But yeah, it's pretty cruel actually, but whatever. Right, you got two things spaced apart. The 1.08 times 10 to the 4 meters apart. Debris is moving that way, satellite's moving that way. I'm guessing the planet is over here somewhere because the satellite's orbiting the planet, so the debris is sort of getting shot straight up into space. It's asking what's the distance between the center of mass and the satellite. So what we're going to do is we're going to do something cheeky. We're going to find out how far, we'll guess where the satellite are the center of mass is first. So I'll just move that down so you can see. I'm guessing, because that's way heavier than that, well, that's 150 kilos, that's 20 kilos. I'll just write that in, 150. It's going to be somewhere about, I don't know, here-ish. COM. That's roughly where it roughly will be. What I'm going to do is I'm going to set up my Cartesian coordinate system. So I'm going to go, that is going to be the Y, and that is going to be, I'll make this negative X, and this is going to be positive X. You need to set up your coordinate system. So basically our zero, our origin, is at the satellite. Because it's asking how far the center of mass is. Well, it's just asking this distance here. So basically it's asking a scalar product, not a vector. It's not asking whether it's positive or negative in the x direction that you determined. But anyway, so you just write out the formula XCOM. It's in your formula sheet. Where is it? There it is, right there. That's your center mass formula. X1 M1 plus X2 M2 divided by the sum of the masses M1 plus M2. Just basically that moment plus that moment divided by the total mass. Moments are masses times distances. So we got 0. I'm going to do the moment of the satellite first because it's at the origin, so there's 0 distance, 1.5 times 10 to the, was it 2? Yeah, plus 20 kilo. No, wait, hold on. Whatever. I'll just do 20 kilos first. I should have done the distance. Times the distance. 1.08 times 10 to the 4 divided by the total mass, which is going to be 170 kilograms because it's 150 plus 20. And then it's going to give me 1,270 meters, which that's 10,080 meters. Yeah, it is, because it's 10 times 10 to the 4, so 10,080 meters, 1,270 meters, that's 10% of the way. Yeah, that's pretty much where we've guessed it, about 10% of the way. Right, describe the motion of the center of mass of the system as the debris in the satellite continue to move along their path. They always have this question. I'll pause the video, write the answer, and then go over it. So what I've said is it will move with constant speed and constant direction if no external forces are acting. This is kind of a very strange question to answer because typically every time you get given these questions it's not under a gravitational field. So I've said likely only constant speed as it is in circular orbit. Gravity is changing its direction. Normally you don't have to worry about gravity, but in this case it's kind of a funny one. The answer schedule was a bit vague. I even looked at it and thought, okay, I wonder what they said. And they said constant speed and constant direction in the horizontal plane, which even then, yeah, it's a strange one to sort of answer. Typically it's always just constant speed, constant direction, unless there's an external force. So yeah, just whatever. Right, debris collides and becomes embedded in the satellite. Calculate the speed and direction relative to the initial direction of the satellite. And embedded debris. Right, this is just going to be a momentum question. You're going to have momentum vectors, you're going to add them together. Probably a little bit of Pythagoras. We'll look at that, they're right angles, so you can use Pythag. And you're going to use a little bit of trig to find that relative direction of the satellite. So what we should probably do is a vector diagram, probably down here somewhere. That's why they're giving us a space. You're going to need a ruler. We're going to be neat. And we'll draw the satellite first. So this is the momentum vector of the satellite, which is probably going to be a whole lot bigger than the debris. And this will be the debris. Just going to the right, something like that. Obviously to scale, because whatever. So we started here. This is our starting point, and this is our ending point. So this is our final resultant vector. And we'll call this, I don't know, P total, whatever, because that's the total momentum. This is going to be the momentum of the sat. I shouldn't be using capital P's, but whatever. Momentum of the, as a lowercase p, I'll just put a subscript, of the debris. There we go. So we're going to find this angle theta. Ooh, whoops, theta. We need that, and we need to find out this V total. So we're going to find P total, and then we need to find that velocity. So we just divide the total momentum by the total mass, and that'll give us a velocity. So first and foremost, we'll quickly write. I'll pause the video actually, write everything we've got, and then start again. Right, so it says the satellite and the debris have the same speed, which is kind of helpful, but not, you know, don't need it to be that case. And we know the masses of both, so momentum equals the mass times the velocity. That's just year 12. Down here we see that this is a right angled triangle, so in other words P total is equal to this squared plus this squared, so we're going to write that there. Alright, momentum total squared is going to be equal to PS, I must put PS squared plus PD squared because I shorten it. And in other words, P total is going to be equal to the square root of 150 times the speed 713.27 squared plus 20 times same speed 7613.27 bracket. I need to keep this way longer, squared, and that'll give you a total momentum of, what is it, 11,52096.808 kgs. And what we need to do now is V final, VF is equal to momentum total divided by, this would be V total divided by the mass total, which is just going to give you 6,777.04 meters per second, -1. And then now what we're going to do is, this is the adjacent, this is the opposite, that's the final speed, opposite, adjacent, tan theta is equal to the opposite divided by the adjacent, but it's going to be PD divided by PS. In other words, theta is equal to tan inverse, what do we got, PD divided by PS. And if you substitute those numbers in, so PD is a debris, it's that number there, PS is the satellite, that's that number there, you substitute that in, you'll get, what is it, 7.60 degrees to the right. RGHT. And I'll just put V total down here. V total is 6,780 meters per second.